Hi everyone, thank you for coming to the Create seminar. Yep. Good to see you all. I'm pleased to introduce our speaker, Dr. Lei Lui from ETS. I had the pleasure of meeting Lei a few years ago at a conference organized by Joe and Xiaoming Zai at University of Georgia about AI in science assessment. So I'm thrilled that she's come here to tell us more about her interest and work. Before I introduce this, the speaker, I've been asked to give a couple seminar reminders. The first of is our next generative AI series is this Friday, Teaching and Learning with Generative AI at noon. And that's going to be given by Dr. Wenjun Huang and Weijin Yu from Purdue. And then our next Create seminar speaker is Dr. Maxine McKinley de Royston from the University of Wisconsin, and she will be here Wednesday, December 4th at noon. So our speaker for today is Dr. Lei Lui, who is the Director of Research in K-12 Learning at ETS. She earned her PhD in Educational Psychology from Rutgers University with a focus on educational technology. Her research interests lie at the intersection of science learning and assessment, learning sciences, and educational technology. She has been leading multiple projects funded by the NSF and IES that capitalize on what is known about cognitive processes, epistemic practices, and peer-to-peer communications. Her projects focus on how to assess science proficiency, including using three-dimensional assessments and learning progressions, and how to use classroom innovations like simulations, AI-based scoring, and feedback to support learning and teaching. And so her talk today is AI for Smarter Science Assessment.
So first of all, it's been a great honor to have this opportunity to share my research here today. So thank you, Kevin and Joe, for inviting me here. As Kevin mentioned, the topic for today is definitely very familiar to many of you. AI has woven itself into our everyday lives in fantastic ways, I would say. Just the other day, I heard my 15-month-old daughter saying, "Hey, Google." And it just struck me how ubiquitous this technology has become in our daily life, and even for those just beginning to talk, right? So while the presence of AI can raise both excitement and concern, today I want to focus on the positive side of AI and how that is how we can harness AI to make science assessment smarter, more personalized, and better suited to meet individual needs. So rather than present a series of findings here today, my goal is to use my studies as a springboard for discussion, exploring how we can build on this work to shape the future of research in the AI-driven field. So today I'm excited to share how AI is opening up new possibilities for scoring and interpreting student data from science assessment. Through two studies, I will illustrate how AI can transform our understanding of student learning in ways that are not only efficient but also insightful. In the first study, we explore automated scoring of object-based models created by students to demonstrate their understanding of the structure and properties of matter. Imagine students are drawing. I think some of you already have been doing work in the similar area. So we are really trying to figure out what's the meaning in students' models. So by using AI to analyze key features of these models and comparing them to scores given by human readers, we can begin to see how students are thinking right along a learning question that we developed for the core concept of matter. This approach holds the promise of providing real-time, interpretable feedback that can support both students and educators. In the second study, we will dive into machine learning techniques to uncover reasoning patterns aligned with the three dimensions of the NGSS, and many of you are the authors of that standards. Here, we are looking at how students respond to complex science questions and using AI to detect those reasoning patterns that students employ when they are addressing those assessment questions. This approach allows us to not only identify patterns, but also gain a deeper understanding of how students engage with core scientific concepts and practices. So I won't talk too much about these 3 dimensions. I think many of you are very familiar with this already. So we all know NGSS has been out for over a decade already, but the fact is that many teachers and students are still struggling with these 3 dimensions. Then how can we help? So we think AI might be able to play some role here. And there are 3 popular ways thinking about using AI in science assessment. One is to automate task development or item development, item generation. That's one way of using AI. The other way, the second way is to automate the scoring or interpreting student data. The third way is to generate automated personalized feedback. So today, my talk will focus on the last 2 focuses. So for the first study, we are looking, the assessment that we designed is focusing on scientific modeling. So scientific modeling is a core practice or essential practice in science. It involves both creating and applying models to deepen understanding and solve problems. On the generative side, scientific modeling allows us to construct models that explain the mechanisms underlying complex systems, for example. It can also represent data in ways that describe observed phenomena, and also it can refine existing models when new data emerges that challenges or enhances our current or original understanding. Another important aspect of modeling focuses on its use and evaluation. That is, we can use models to explain and predict related phenomena, and use computational or statistical models to generate or test hypotheses. And also we can use models to evaluate a model's its explanatory and predictive power. So in this assessment example, we developed a modeling tool that enables students to visually demonstrate their understanding of particle models related to the core idea of matter. This task was part of a scenario-based assessment in which students were tackling the challenge of purifying ocean water to obtain fresh water. Specifically, students were prompted to create models that represent ocean water and pure water at the particle level, illustrating the smallest unit of matter. So we used a learning progression for matter to evaluate the models students created, providing insights into their understanding at various levels. At this lower anchor in the learning progression, students typically will describe ocean water using macroscopic components. This often includes drawings of water, fish, or even steam above the ocean surface, indicating their initial observable understanding of ocean water. Then at the next level, students begin to incorporate both microscopic and macroscopic elements, a model that we refer to as the raisin in the pudding model. Here, students draw a mix of visible objects such as water drops, along with representations of water molecules, and sometimes even fish swimming in the water. So you can see a mix of both macro and micro objects in their drawings. And then moving to the level 3, students starts to adopt some kind of particle-based model using abstract symbols to represent different types of water particles, though they may still hold some naive ideas. For example, a student at this level might use color to differentiate between particles, such as in this case, the students are using red dots to represent warmer water, but then they're using green color to represent cooler water. So this is a typical naive idea that students hold for this level. And then finally at level 4, students demonstrate a more sophisticated understanding. They incorporate particle behaviors into their models, such as using arrows to depict particle motion, indicating a more dynamic and more deeper understanding of matter at the macroscopic level. So this is a learning regression that we try to use to map some of the students' drawing features with some of the level descriptors, characteristics. So in this slide, you'll see that to automate the scoring process, our team of both learning scientists and NLP, which is natural language processing experts, mapped specific features in students' drawings to corresponding levels in on the learning regression across 4 key aspects. This involves both JSON-based data analysis and also image processing techniques. By aligning these extracted features with the level-specific characteristics in the learning progressions, we were able to automate scoring in a way that reveals students' conceptual depth and progression. So in the first aspect about scale, we trained the system to recognize whether students used macroscopic or abstract symbols. When abstract symbols were used, the algorithm also make decisions whether they actually represent the microscopic particles or were simply using them to form a larger macroscopic object. So sometimes the students would use the square or dots to draw a fish instead of picking the fish from the macroscopic pool. So we have to develop some algorithms to identify that. Then for the material identity aspect, the model identified the different materials represented in students' drawings, discerning the identity of various components in the model to see if they align with the scientifically accurate representation. And also we can train the machine to analyze whether students depict particle behaviors such as movement or interaction, which provide insights into their understanding of dynamic molecular processes. And finally, the distribution, in terms of the distribution of particles, the machine can count how many particles they are including in the drawing and also calculate spatial distances between the particles. The system can assess how particles were distributed across this drawing. So these are some of the features that we human defined, to train machine to pick on. We tested various regression and classification models to see which best matched human assigned scores using quadratic weighted kappas, which is QWK here. So our results showed that regression models generally outperformed classifiers in predicting learning regression levels. Particularly for the linear regression, achieved the highest QWK score of 0.624 as represented in this table, making it the most reliable model. And the next reliable model is the random forest regression, which is, I think, the QWK value is 0.623, so it's very close. But for some reason, this model showed slightly higher prediction variance. Then the SVR, I think the support vector regression model showed a moderate agreement with the QWK of 0.551, while the decision tree regression lacked with the QWK of 0.517, which I think is a bit too low, but then and also with very high variability here. So in summary, linear and random forest regressions provided the most consistent and accurate predictions, offering a promising approach for automated learning regression level assessment here. So for this is, I would like to also pause a little bit here to help us to think about when we talk about machine scoring versus human scoring. One thing that our team actually discussed a lot is about what is human good at, what is machine good at here. So when we compare human and machine strength in scoring, we see how each bring unique advantages to the process. For human, we excel at handling ambiguity, such as recognizing partially correct models and making holistic judgment about particle behavior, this skill actually allows humans to grasp the broader context and nuances in student responses. While for machine, on the other hand, offer consistency and precision. They are highly effective at identifying nanoscale particle representations, recognizing specific particle patterns for different states of matter, and performing detailed calculation of particle types and distribution. So we think we should leverage both advantages here when we are doing scoring. So one of the potential for a hybrid scoring approach is to combine the strengths of these two. Scoring could be more optimized in our view. For example, machine can pre-score some of the models on object criteria like the scale, particle distribution, and then we can have human review, particularly for the holistic scores. So this is some of the things that our team has discussed in terms of how to identify the strengths in terms of human versus in terms of machine, and how we can combine those strengths here. So I'm going to pause here for any questions for study one before I move on to the second study. Yes.
When you looked at the combination or the inferred combination that needs to be done between human and machine strengths, first of all, it's not something we know that machines going back 40, 50 years have their blind spots, so to speak, and humans in bad positions are better to compensate for. How do we streamline this? Or how can we, so to speak, meta AI in order to require less and less human integration, okay, to have people, in that case teachers or evaluators, be focused on what's really important, finding the larger schemes for the machine to implement. So how would you?
That's a good question. So one of the things, I think there are two parts. One is that when we say combining, it could be combining different parts, right? So the machine will focus on something that they are good at, and then a human can focus on something that humans are good at. That's one way of thinking about combining. There will be less interactions there. But then the second approach is more think about really integrated approach, where I think we have the machine pre-score something, but then human will check the accuracy. So in that way, I think a good analogy to use here is more think about data cleaning or data. When you do data merging, you always want to check if computer has made some mistakes there. So we would randomly check some of the rows in the data set to make sure that there is no misalignment in the rows. So I think human will be playing some of the quality control role in the process. But I think the point of getting human involved is more focused on the checking the accuracy or finding errors. But the first approach is more really think about the combining the strength of both human and machine. Hope that answered your question to some extent.
So was the background of this kind of a summative assessment sort of framework where you're just trying to evaluate an individual assessment instrument, or was it more formative? And my reason for that is to raise this interesting question, right? With a formative assessment that's recursive, right, where the students get the assessment back and whatever, the students are going to adapt to and begin to manipulate the AI, right? And so I want to raise that as kind of a question in terms of the research.
It's a great question. We actually had a lot of inspiring chats with your colleagues here, and we talked about the different purposes of assessment. So this actually, your question definitely addressed to that. So in this context for study one, the assessment was used for classroom purpose. So it's more for formative purpose. So I think the reason that we're using the automated scoring is for the purpose that we can provide more timely feedback or timely level assignment during the instruction instead of wait until the end of the unit. So I think we are, of course, once we have that, the feedback will be entered into the assessment, and when students or teachers get that feedback, they can refine or revise their models, which I didn't show in this presentation, but I think in the assessment there are multiple points where students can refine their models based on the feedback that they got.
Right, so that raises this interesting question, right? Because given the machine strengths, right, if I were a student getting negative feedback because I did macroscopic stuff, I would just select more of the individual particle things because I get a better score. I wouldn't necessarily have developed a better model, right? But I would be recursively responding to and manipulating the AI's grading scheme, right?
That is possible. Talking about ETS, like we have started with automated scoring for the past 3 or 4 decades already. When we started with TOEFL, GRE, I think we are automating the scoring for those essays, right? But then I think we have a lot of hesitation to reveal some of the features that we are using in our AI model, because those features can be easily manipulated by students when they are writing or they are taking the assessments. Like for example, if the length of your article will play a big role in your score, the students can just write more, right? So or if you have more overlap in your essay versus the question stems, that's what the data show. So this is something that Joe and I were just talking this morning. Like we feel like we really need to think about the theory behind the AI model, which can explain the data, which I believe will be the human-driven type of a process instead of AI-driven process. So I think we'd rather to make sure that human can actually interpret the pattern instead, so that I think it's less manipulative in the sense that not just adding 2 more dots there, then you'll get higher score. But it's more about the meaning of why you need to add 2 more dots here to show, so that the distribution or the density of the particle actually are more like a solid rather than a gas, right? So I think that's the meaning part is important to be incorporated into the feedback. So what we are providing to the students is not just a level, but really there will be some descriptive information there to help them about the why you got 2, why you got 3, because you are missing this, and why the missing piece is important for the deeper learning. I think that's key to be included in the feedback. So some of the feedback that we got for our work is that when we are developing the feedback system, we need to have a framework to guide the development of the feedback, which I think when we generated this, we were more focused on the automated scoring piece rather than how to provide the feedback to students, back to educators. I think your question actually is related to the feedback that we got. Yes?
I have a concern about combining human and machine scoring. So in a small classroom, so it might be very helpful for the instructor to identify the problem and to when scoring the homework. But when it is implemented in a larger scale, for example, in the GRE essay, TOEFL essay, so the graders, they don't really know the student, and so when they grade the essays, for example, based on and looking at the AI score, so would that be more time consuming, because they need to look at two things. One is the student's essay, and then the other is the AI feedback. So they need to think about the essay twice. So that's one of my concern about using the machine to help human scoring. So personally, I think AI is a tool to help with improving efficiency, but in the larger scale, it might be possible. It is possible that it is impossible. So this is one of my concerns.
So yeah, I think your concern actually also relates to the discussion about the different purposes of assessment. So for a classroom, particularly in terms of involving teachers, right? So that's more for, we are hoping to get more formative feedback that teachers can provide back to the students. for that case, I think it's worth the time for teachers to spend the time to make sure the feedback makes sense or actually are related, at least were accurate when it's before sending back to students. So I think having teacher in the loop to customize the automated scores or the automated feedback, I think that's necessary. But then for the other purpose, like for GRE, TOEFL, this kind of large scale or summative assessments, then I think because of the purpose of the assessment is trying to evaluate. So I think it would be worth for us to focus on the accuracy part, because for ETS, just from the organization perspective, if we get like some errors in the score, ETS can be sued and can be broken in a few years. So I think that's the practical issue that we're facing. So we have to make sure that the AI. So this is why I think ETS we are very hesitant to use AI to a lot of the large-scale assessment, because we have a very high bar to achieve in terms of the accuracy. And we actually got some complaints from our clients saying, why you cannot always use AI? We said, because we have this high bar, and then the client will say, can you drop the high bar here? I said, no, we can't. So I think that's for the purpose of the large-scale assessment, particularly high-stake assessment, I think it's very important for us to make sure the AI scores are accurate.
Thank you.
Sure. You have a question, Sarah?
Yeah, so I guess one thing I'm wondering about looking at this list of human strengths and machine strengths is like, with the human strengths, we're talking about the ambiguity, handling the different contextual factors, and it kind of makes me wonder about the objectivity piece. Like, what does it mean to say that the machine can be objective when we recognize that there is this ambiguity and this contextual factors?
That's a good question. So for the objectivity, what I mean here is that, let's say for ocean water, there are sand, there are water, so there are many different types of particles. For human, it's look at the example that I provided earlier. So for level 3, so it's very hard at least it would take human much longer time to count how many types of particles students are trying to represent here. But for machine, it's very easy, and also it's very quick, efficient, that they can count that very easily. So that's objectivity, strength of machine. But in terms of ambiguity, then what does the red dots mean? Or what does the green dots mean? So it's very hard for machine to identify, because sometimes you never know how students are trying to represent those. But then for human, I think we have a better way to address ambiguity. Not saying that we can always address that, but I think there are ways that strategies human can take to tackle that ambiguity. Okay, so now I'm gonna move on to the second study. So for this one, this is the one that we are, based on our prior NSF grant, so we are actually trying to use AI technology to identify students' reasoning patterns. And indeed, by reasoning pattern, we actually mean the typical ways of students thinking when making sense of a natural phenomenon or solving a science problem. So in research, there is a lot of research on how experts think, or what's their reasoning pattern, but not much on student reasoning pattern. So this is, I think, the selling point for our grant. So I think we're really focused on the student's point, and also we do believe that students did bring a lot of reasoning strategies into their science learning, but we may not have leveraged that enough in our instruction. So we think that this reasoning pattern will be essential for instruction, in the sense that those can become essential stepping stones to use and interpret student data in their sense-making of science, and also it can become the foundation for evidence-based instruction in response to what or how students know, instead of just correcting students' understanding there. Like I mentioned before, the research opportunity here is that we're trying to fill the gap here to focus on students' reasoning. So for in this example, again, this is a scenario-based performance test that we developed through another IES grant. So in this it's called dot cross. The project, the title is called dot cross. So in this item, students were interacting with a simulation where they can see how ecosystem actually components interact with each other. So in this case, it's about the cornfield ecosystem. Well, in one year, they get invaded by corn rootworm, and then the corn harvest jobs. So the simulation actually simulate that phenomenon, and then we are asking students to come up with an explanation to say whether adding harvestman, which is an insect that can eat the rootworm eggs. And I think we're trying to ask students to reason about the system components and also the interrelationships of those components. So that's the background of the assessment system. So the reasoning pattern that we're using, I have to say, is very preliminary at this point, where we're trying to identify, as we talked about earlier, that students and educators still are challenged by those 3 dimensions. So we are hoping that the AI can provide some kind of help for educators to identify which dimension the students bring into their reasoning process. So for pattern 1 and pattern B are both unidimensional, but pattern A is more about focusing on the practice only. So students, this is also the issue about integrating the 2 dimensions, right? So many students and educators are facing that challenge. And our data also showed many students' responses fall into the pattern A and pattern B. Either they only cite the data without thinking about the science behind that, or they would recall or just cite some of the science principles here, but not connecting to the data presented here. So of course the 3rd pattern, pattern A plus B, the multidimensional reasoning pattern, is a mix of both dimensions. Given that, we think there are some opportunities for us to further fine-tune this pattern, in the sense that we found sometimes students would include both the practice or the content into the reasoning, but then they're not connected. So how the principle connects to the data, I think that's one issue that we didn't address in our NSF grant, which is something that we're trying to address in the current IBS grant. And also we have around 20% of student data which is treated as unidentifiable. I think that's the part where we found responses are either too vague or they are irrelevant to the question. So these are the 4 patterns that we have used. So I'm going to show a short video just to introduce the proof of concept study that we did with NSF grant.
The SPIN NGSS project aims to develop an automated tool to support student reasoning in science learning. In the previous stage of our research, we used student responses to identify and predict patterns in student reasoning. We also developed an annotation tool to highlight evidence related to 3-dimensional learning. Pattern 1, reasoning focusing on data only, related to the NGSS practice dimension and represented by blue highlighting. Pattern 2, reasoning focusing on conceptual mechanisms only, related to the NGSS disciplinary core ideas and cross-cutting dimensions and represented by orange highlighting. And pattern 3, reasoning with both data and conceptual mechanisms. This video focuses on the additional project progress, including developing an AI-supported tool with immediate feedback and conducting a cognitive interview study to explore how students use the feedback to revise their responses. In the study, an AI model was embedded in an online tool that generates real-time feedback for a selected constructive response item focused on ecosystems. We also conducted cognitive interviews with 45 middle and high school students. The study investigated how students made sense of the real-time feedback and if or how they made revisions after receiving feedback. We found 49% of students' initial responses were diagnosed as pattern 1, 11% as pattern 2, and 38% as pattern 3. After receiving the immediate feedback, 96% of students who received patterns 1 or 2 made revisions to their initial responses, and 69% of the revised responses were changed to the more sophisticated pattern 3. During the interview, many students expressed that they enjoyed the task and found the automated feedback useful for refining their initial responses. Several students highlighted that this was the first time they interacted with an automated feedback tool. We also learned that many students didn't receive direct instruction on the NGSS dimensional terms. Therefore, students suggested we provide examples, particularly for scientific principles. This AI-supported online tool could be useful for supporting three-dimensional science learning and teaching in classrooms. Our current AI tool includes automated diagnosis of student reasoning patterns, immediate feedback, and opportunities to revise based on the feedback. Future work may include the development of a teacher dashboard for class and individual level reports of student growth. We plan to pilot the tool in real classroom settings.
So for this study, we are the automated, the AI piece is focusing on, so we're using 3 phases to develop the AI models. In phase 1, we're trying to predict the reasoning pattern label or create the automate the reasoning pattern label. So we compare 2 approaches. One is the traditional machine learning, which is SVR, and with features based on sequence of letters or sequence of words and syntactic and functional relations between words. That's the first approach. The second approach we used is the deep learning, which is a BERT model developed by Google AI, trained on a huge corpus of English and fine-tuned using the responses in our student responses data set. So we evaluated and compared using 10-fold cross-validation. Basically we trained 10 models, each 90%, and of the data is evaluated on the remaining 10%. That's the approach that we took. And we evaluate the 2 approaches based on this, based on both the accuracy and also macro F scores. So you can see that then in phase 2, we try to predict the spans of the text that we mentioned in the video, where we're trying to show the evidence of why this response is pattern A, why this is pattern B, etc. So we also use the, let me get this right, bidirectional gated recurrent unit network with conditional random fields. Again, that's a fancy AI term here. So I think what we're trying to do is trying to improve the accuracy and trying to find the better approach to, in this case, which is a BERT, is the better approach in our data. So I think we're trying to improve the accuracy of the prediction here. So this is like we said, this is because this is a proof of concept, so we didn't focus on the UI/UX design. So this is a very ugly UI/UX design, but you can see the components what we included in the automated annotation feedback is we want to provide the color coding for each dimension. We want to also provide the reasoning pattern label, as we mentioned. We also provide prompts to help students revise their responses. It's very interesting that, as I mentioned earlier, that how you provide the feedback really matters. We have some of the students, and also maybe also based on how students perceive feedback in their classrooms. So I think some of the students actually, they had A plus B response in the initial phase, but then when we provide feedback and probe them to elaborate more, they change back to only unidimensional. Because when we interviewed the student later, and they said they did something wrong in the first one. So I think in the past, students were used to think about feedback as correcting them. But in this case, we are not trying to correct their response. So I think this is some of the misconceptions students have on feedback. So I think it really informs us to think about how we can provide feedback better. One is to acknowledge what they can do or what they know, and second also to focus on some of the improvement areas. So I think we need, in this case, we didn't separate those 2. So I think it's important for us to really rethink about how to redesign the feedback. I'm going to skip this one because I think that we sort of covered that in the video already. So here I want to show some qualitative examples about the discrepancies in human versus machine identification, and I need you to help me to also interpret why you think this discrepancy occurred. So this is the first, is that big enough for you to read? So this is the first example. You can see the top one is actually the machine score, but then the bottom one is a human score. So you can see the human identified targetmen were outnumbered, but then the machine didn't consider that as like a data pattern that's shown in the graph. So this is one discrepancy that we example that I would like to share here. Why do you think this happened? Give it a try.
Great. Just thinking about my students. Part of how they learn to structure the answer to the questions is something they learn in grade school.
Mhm.
Please repeat the answer. Sorry, repeat the question. So, what I'm looking here is partial data and trying to, me as a teacher looking at it, I'm immediately completing the relevant part of the question to structure the answer accordingly.
Mhm.
The machine doesn't have that input, it also only works by the relevant rubric. And so it misses a lot of connecting words, and you also get your the answer that can be attained to specific elements in the NDSS. And so let's call it hit on specific targets that coming together will make a higher score. But again, the human equivalent or the human outlook on this will be, okay, this is missing severe elements or just really important elements. So I would ask you a return question if you don't mind. I assume, I'm missing the question. I don't see it, it's just the answer. So I assume that the student will see the question and then a blank box to answer
Right.
this answer. So I would ask, were the students instructed on how to answer questions in the twisted sense?
Right. I think your point is really valid, that how the task or the item were designed will impact what kind of reasoning patterns students may show or bring into their response. In this case, I think our questions are very much focused on providing the simulated data there. So that's why you see that pattern A really is the top pattern that many students are using, because it's data focused, and also because the question actually we're asking them to use the data, right? But then in the we also did the same thing with another item from the California State Assessment, and which one I think they didn't provide a lot of data, and then you actually see the reverted pattern ratio in the pattern A versus pattern B. We would see a lot of like content citation or recalling versus the data use. So they definitely how items are written will impact the reasoning pattern. I totally agree with that. But in this case, actually, what the problem is that we don't have many students use the term outnumber. We have a lot of students say harvestman is more than the rootworms, or they have harvestman cannot eat all the rootworms. So I think that's the common ways that we have seen in students expressing. The next one actually it might be a better example to show some of the discrepancy here. You will see the top one said it's the same response. So the top is a human coding. Maybe because the harvestman ate some corn too, but then the machine didn't highlight this, but human highlighted that because something is something. That's a sort of like the relational statement. So we would code that as more like the mechanical statements here. But then machine couldn't capture that because in this case, harvestman was misunderstood by this student. They thought harvestman was a human who are doing harvest in the field instead of an insect, even though we provided definition in the assessment, you know how students read, right? So I think in this case, the AI didn't consider the vocabulary gap in students. Rather, they are too much focused on what's the existing system components or system relationships. Which one? In this case, if you misunderstood harvestman, then AI won't be able to find that in the pool of the relations because the harvestman versus the corn, most of the existing data doesn't include that relationship. So you can see that it's really about some of the issues that I think Kevin, your team is trying to address about the imbalanced data, right? So we don't have enough, or we don't have balanced data to show these patterns in student response. Then AI cannot identify that feature or that pattern correctly. So I think this is one issue that we found in our study. So this actually relates to some of the thinking about the future. What should we do to address some of the issues that we identified when we're trying to develop some of the AI innovations. So then first, what can AI support? I think at least these are some of the basic. Of course, I didn't try to include some exhaustive list here, so I tried to use some high-level support that I could think of, like support teacher use of assessment data, which is to improve their assessment literacy as well, so we can make that more timely and also more instructionally relevant. Right? That's one support that AI can provide. The second support is that AI can help teachers better use of their time to focus on individual instruction and provide feedback. So we are trying to take away some of the easy tasks for teachers and then ask them to focus on the really things that matter to the students. So notice I put support and help instead of replacing teachers. So I think it's really critical to have teachers in the loop as we are developing any AI innovation. Then what's next? So for our study, we are trying to design and conduct teacher training on use of the AI tools and feedback customization. We also try to conduct some pilot and field classroom studies to iteratively refine the innovations and investigate teacher-student perspectives on implementing these assessments. And finally, we also want to explore some development of the generalizable AI algorithms. I think in many cases, many of the algorithms are item-specific or task-specific. So we are trying to do that through two new grants. The first one is the IES grant that we just got this year. So for this one, we're trying to address three kind of validity questions. One is about cognitive validity, second is about inferential validity, third is about instructional validity. So basically we're trying to see how valid our assessments with the AI tool is. This is one grant. The other grant is the grant that we got with Xiaoming Zhai from UGA, University of Georgia, and then for that AI Center grant, we're trying to address the need for both the disciplinary, interdisciplinary, and computational education for middle school students. And also we focus on designing Gen AI, particularly, as we mentioned, is to have teachers or educators in the loop kind of approach. Those agents should serve as a mentor, learning buddy, collaborative learning agent, and teacher assistants. So you can see it's playing a lot of roles. So we're trying to explore how to develop those agents and what kind of theoretical framework can guide the development of those agents. So again, the purpose is not trying to replace teachers, but rather these will become assistants to teachers when they are working with students. So I'm gonna pause here for questions. I think this is the end, my last slide. So thank you, and let me know if you have any questions or comments or feedback. Yes, Kevin.
So on your second study about the reasoning patterns, you talked about accuracy of the patterns, I think, but there's also the accuracy of actually the highlighting of the evidence. So can you talk about that and whether students actually reference that in your cognitive interviews? Did they mention exactly what was highlighted? Like, I'm wondering if that helped them in any way or whether that was actually confusing in some way.
The highlights definitely actually help the students to refine their responses, because I think because it's an interview, so we were able to probe them also to think about the meaning of the colors in their response. And some of students got that you have to have two colors to have a better score or to have a better level there. So I think they got that. But I think relates to your question about what does that mean? Yeah, are they trying to game the system here? I think yes. I think the current UI UX is not, and also the feedback system wasn't really good enough to achieve that goal yet.
So it's somewhat related to the second question, and maybe I misheard you. It seemed like once the students got feedback from the AI, their scores improved tremendously,
Yeah.
right?
Yeah.
But when I looked at your prompts, the prompts are very generic.
Yes.
And I find that almost hard to believe that those generic prompts saying, elaborate this more would cause such a drastic change. That just caught my eye almost instantly. Like how, I mean, there's a lot in the literature that actually says that generic prompts
Won't work. Yeah.
don't work,
Yeah.
right? And yet you showed me 3 very generic prompts that can be used with any assessment task out in the world, and yet you showed dramatic changes.
Yeah, we have 69% of students actually change their responses.
Yes, I don't
Yeah.
understand
And the thing is that the prompts that we provided are very targeted. Like for example, if they have pattern A, we're pointing that how about the science principles? Can you link the science principles to the data? So that's the part. So you're basically telling them what to add, or at least the direction of revision. I think that this is why we see the majority of students actually were improving in terms of the reasoning pattern, but that doesn't mean the quality of the responses itself is higher, because like I said, even they get A plus B pattern, sometimes the response is like very forced, like integration of A plus B, but then you don't really see the connection. But then we didn't really look at the connection between what's being cited in the data, or whether the science principle that students use actually are able to explain that pattern. This is what we need to do in the current grant. Yes?
I had a question about how you define the things that you, the machine code. So
Right.
the question where it said, where the answer was the harvest memorandum number,
Right.
and that was coded as an SEP. Is that not a machine? Or?
That's a mechanism. Even though it's not in the mechanism that the harvestmen ate corn, it's not.
No, I didn't mean that one. I meant the one with the harvest memorandum
Oh,
number.
outcome. Oh, that's the data. Yeah, that's the pattern A. Yeah.
So it was so it was coded as a scientific practice.
Yeah.
And was, but I guess in our work we would not call that as a practice because there's no reasoning in there.
Right.
So how did you decide that that was a practice? I guess my question is how did you decide that's a practice?
I guess it's the question. So for our SEP, the definition here is more focused on the data citation or data use here. So it's not really focused on all the SPs, like including explanation or argumentation. But in the new grant, we are actually focusing on the argumentation piece, I think, which will require more about what can be counted in as SCP. Yeah.
All right, that makes sense. Thank you.
Sure. Kevin, I think to your question about the color coding piece, the span part, I have to acknowledge it's very hard to achieve very high reliability for the span, because I think the way that how machine is learning, they're picking on the keywords or the sequence of the words. So many times when human code, we would highlight a set, like a whole set of phrases here. But then because how AI is learning from that, the AI span is very segmented. So they would pick 2 words, 1 word here, 1 word there, and show as examples. So we didn't really even bother to try to achieve the reliability there. But if you have any suggestions in terms of how we can improve that, I think we definitely would like to know.
Sorry, no, just to follow on, that's what I was sort of thinking about might be confusing for students if they see
Right.
punctuated highlighting for pieces that they think maybe
Right.
are more connected, at least how they wrote them or intended them to be. Like
Right.
whether that can actually be confusing for students.
It could be, this could be something that human will be good at, like we always have some continuity in terms of, highlighting something, but then for AI, it's very segmented. Of course, we can define AI to say we have at least 5 or 4 words, but it's kind of arbitrary to set that rule. Yeah,
So the 2 studies that you showed, those were not with generative AI, they were
No.
with deep learning.
it's all,
right?
machine learning.
Yeah, yeah. So, but this new one is with generative
So
AI?
for the first grant that I talked, this one will be still, it will be a combination of machine learning plus generative AI. But then for the one with Xiaoming, UGA, that's more focused on the Gen AI.
So related to that, I wonder if you'd speculate ultimately where this is progressing to. So far this work seems to be mostly focusing on what I would call a teacher agent, right? Something to assist, an AI engine to assist the teacher, right? Ultimately, I think we're going to see student agents as
Right.
well that have to interface that way, and so, which might offer some really interesting additional affordances, right? So where do you see this progressing to as we continue to build out these tools?
So the learning buddy or collaborative learning agents, that's more for students in the Gen AI Center grant. But for the mentor or the teacher assistants, that's more targeting for supporting educators. I think we were a little bit hesitant to push that directly to students without some customization by educators. So we always want to focus to go have teacher in the loop to make sure that they actually have some kind of scrutinizing about the accuracy of AI first before it can be pushed to the students. That's our concern earlier, but I think with the Gen AI, I don't know, maybe we can get there.
All right, another question then.
Yeah.
So I completely agree with you that
Uh-huh.
there's a real danger in letting this loose in the classroom, but it's already loose, right?
Right.
There are a lot of publishers that have already
I'm doing
released
that
this,
already.
without any testing and without any research. Do you have any worries about that?
Of course. I was talking about all my worries since yesterday about using AI. Even though my research recently has been more focused on the AI applications, I have big concerns about some misuse of AI or some of the, I think, without really further validation or kind of use of AI. Melanie, as I mentioned to you, some of the work like using AI to generate instructional materials without any theory to guide that, that's just so dangerous, right? We just, generate some really crappy stuff, and it won't really do any good for our students. So I think that's really something that we should avoid. This is something I emphasize with Joe, that this is the role of us as researchers to interfere here to make sure that AI, one is that AI innovation is developed in the right way. Second is that also train people on how to use AI in the right way. Of course, I'm not sure that we all know how to use AI in the right way. Like Joe and I might have difference in terms of whether we should have used automated driving, right? But then I think that's the thing that we need to at least bring some attention to people to make sure that these are some of the concerns that we need to pay attention to. Any other questions?
Okay, let's thank